Hello student, welcome back. So in this video lecture we are going to see maximum power transfer theorem. So we are going to prove the maximum power transfer theorem from our lab. So I am going to demonstrate how we are going to perform the maximum power transfer theorem, as well as we are going to perform in a PSpice software to calculate how the maximum power is transfer theorem can be verified from the circuit itself. Okay, so what are the objective for this particular experiment? To understand the need of network theorems, determine the load resistance to have maximum transfer of power from circuit to the load, and to verify the maximum power transfer theorem. So the aim of this particular experiment is to verify the maximum power transfer theorem. So you know that maximum power transfer theorem is maximum power will be transferred from circuit to the load when the circuit's resistance, we can say the internal resistance of the circuit, is equal to the load resistance of the circuit. We have to find out the internal resistance by using Thevenin theorem, and then we are going to find out the load resistance according to our experiment, and we are going to prove that the load resistance and internal resistance are same, then only we are getting the maximum power. So for this experiment we are taking one actually one circuit. That circuit contains resistance R1, resistance R2, resistance R3, and there is an external resistance called as RL. So we are going to vary this RL, according to which we are going to calculate RL flowing through it, or we are going to calculate PL, that is across this resistance RL, and then we are going to draw or calculate the power. Then with respect to the load resistance, we are going to draw the graph of uh, RL will be at the x-axis and the PL power at load will be at the y-axis. Then we are going to draw the graph. So the graph structure will be same like this. So where at this point we are going to get the maximum power. So that resistance RL, that should be the internal resistance. So RI, that should be approximately equal to RL. Now, so to calculate a power, so we have a powers formula as PL square divided by RL, or we can have IL square into RL. These are the two formulas we can use. So in simulation we can use any of the formula, but in practical case point of view we are going to deal with the Thevenin theorem, Thevenin resistance, and then how to calculate the power from that particular two uh, quantities. So open circuit voltage VTH, as you can see my previous video where we have talked about the Thevenin's theorem, same circuit was there. We have calculated VTH, we have calculated RTH. So these are the formula that I have directly taken from that particular experiment. So you can see the load current RL, that is nothing but, you can see here, this is the voltage source VTH, this is RTH, and that should be nothing but equal to RI, internal resistance, for the maximum power transfer theorem. So total current that is flowing through this RL is nothing but the voltage supplied, or voltage supply, that is VTH, divided by the total resistance. Total resistance means RTH and RL, they are in series. So RTH plus RL, this will be the load current. So the power we can calculate RL square into RL. So RL we have VTH divided by RTH plus RL bracket square to RL. So now the power will be delivered to the load will be maximum when RL and RTH, they both are same, or we can say the RI, that both these resistors are same. So we can be verified by taking the derivative of PL with respect to RL equal to 0 and solve for PL. So you can see the maximum power will be delivered PL max, that can be calculated to be as VTH square upon 4 RTH. So where we have taken the derivative of this particular expression with respect to RL, and we are getting a value called VTH square upon 4 RH. So where the RL is tends towards the 0. Okay, so now what we have a power maximum, so we can calculate VTH. Let's look at here, we can calculate VTH from this formula, as we know we know R3, we know R1, we know R3, we can calculate VTH. And same RTH, so we can calculate the RTH as R1 we know, R3 we know, as well as R2 we know. So from that we can calculate the theoretical value of this PL max, and then performing the practical we can have the practical value, and we can compare both of them value, the PL max, as well as we can compare, we have calculated the VTH. So the RTH and RI both are same, so RTH and RI can calculate from theoretical point of view, and then we are going to draw a graph where we can find out wherever the maximum power is, that resistance will be considered to be as RL, that RL should be equal to RI, then we can say that the maximum power transfer theorem is. So look at here how we are going to calculate a VTH. So for that purpose I have taken 5 volt V, R 100 ohm, R 230, 330 and R3 680. So this calculation is already done in Thevenin theorems. So VTH is 4.3589 volt. Here RTH is there for 4.17.17 ohm. So from this you can calculate PL. So you have the formula of the PL as VTH square upon 4 RTH. So H square upon 4 RTH. So as you know VTH, as you know RTH, you can calculate the PL theoretically. So I am keeping as it is for calculation at your end. So do the calculation, then we are going to see how experimentally it done. So while performing the experiment, what we are going to find, so look at here, we have find out RTH is 417. So there is no need to take the load resistance from 0 towards infinity. So we are stick towards the 470 and we are going to take the few readings back and the few readings forth. So back and forth reading will give us a graph like this. So that graph will give us a back and forth reading. So you can see I have started with the 300 degree. You can see we have started with the 300 ohm, then change in like a step of 50, 350, 400, 450, 500, 550, 600, 650 and 700. So these are more than enough readings to calculate to verify the maximum power transfer theorem. So at that each resistance RL we are going to calculate. This is the experiment setup. I have put the V1 as 5 volt. We are connecting it to the input. So same as like Thevenin theorem, we are going to perform this experiment. Only extension is that we are going to connect RL and we are going to vary the RL and measure the VL. So I'm going to connect the VCC 5 volt ground. Then we need resistance R1 to be 100 ohm. 100 ohm. Then the next resistance R2 is actually 330 ohm. Connecting it to output. The next is 680. Connect the 680 resistance ground. What we are going to do now, we are going to practically calculate. We have calculated theoretically, we are going to practically calculate what is VTH. So look at here, the VTH is 4.31 volt and we are going to calculate RTH by just neglecting the power supply, shorting resistance R1 with ground. We are getting VTH to be RTH to be as 0.428 kilo ohm, so 428. So practically, theoretically it was 417, practically it is 428. So we'll have a different reading in case of maximum power transfer theorem as well. So that's why we are taking the step of 50 volt. So 50 ohm. So what we are going to do, we are going to have a load resistance. So this is a resistance box. So what I'm going to do, I'm going to connect the resistance box to the V out and ground pin. So you can see the V out pin should be connected to resistance 1 terminal and the ground pin should be connected to resistance next terminal. So for that purpose, I am going to remove the multimeters positive. First resistance box first terminal I'm going to put, we can put in the resistance box or we can put at the V output, that is in parallel, so we can put wherever we want multimeters positive terminal, then the negative terminal we can put it in the ground terminal or we can say resistance box next terminal. So this is done. So the precaution should be taken to perform this experiment is that the one key from that particular resistance box is to be removed. So I have removed one. Now we are going to put it to 100 ohm. So though I have said that start from 300, so we have the experiment, we can start from 50 actually. We can start from 50 tends towards maximum whatsoever we want. So the reading is not time consuming at all. So I'm keeping on the power supply. Just look at here what we are got it has a VL. So just take pen and paper, or fill up the observation table to draw in your sheet. What is the value of 100 ohm, what was, and then I have put kept the 150 ohm. So observe the out in there. So this is for the 200 ohm reading, so 3.53 volt. So I'm going to increase it with the 50 ohm at each times. See on the multimeter. So now we are going to adjust to 250, getting the 50 out. So 250 reading. So next is a 300 reading. We required lots of reading for this experiment. 350. Note it down. Then 400. So I am going to put all the 115. I am going to have 200, 202. So 400. So 400 readings is here. 450. Then the next will be a 500. Going to put 50 back, 100, terminal, 200, 200, or we can have 500. So this is 550. Then 600. As you know, the VTH is actually 412, 427 practically, 417 theoretically. So we can take the reading up to 800 or 900. That is good. This is 700, 750. Take of 800, then 850, 900, thousands. So we can have that much readings. So it is okay to have that much reading. So look at here. I'm taking again one reading that is of 1050. Now in case of a P-spice, so we can have the same socket, 100 ohm R1, 330 ohm R2, 680 R3. Here is a R4 resistance is considered to be as RL. And if I am doing analysis setup where I am going to do a DC sweep, please watch this video in high definition so that you can observe whatsoever the small font readings are, so small font sizes are. So global parameter I am taking it as RL, 10, start value 10, end value 2000. So in simulation we can take more and more values, and I am incrementing, suppose I am incrementing with the value of 20, and I am going to take it to 1000 only. Okay, so this is okay, close, and I am doing analysis, simulate. So we'll get a graph. So that graph will be considered to be as a blank graph where we are having RL only at the x-axis. So trace, I'm going to add trace. So what is the formula for calculation of power? That is equal to I square RL. So I R4 is RL actually, I square. I'm going to take and the RL. So the formula is I square RL. So IR4 into IR4 into RL, that is equal to I square RL, and I am saying you will get the graph like this. You can see the power is less at like very much close towards the zero, and it is maximum was the, can take like this. You can look at here was, can look at A1 indicate the readings that we are taking. So this is 100 ohm resistance at that time, 7.19 milliwatt actually the power. You can see as I'm taking the cursor the longer distances, you can see here what is the maximum value we have to look. So 11.35, 11.375, 78, 79, 80. Okay, 180, 85, 6. Okay, at 86, We have to concentrate on X. Okay, so 410. What we are getting from the software is the 410 resistance. So this is the way you can do in a simulation, piece by simulation, to find out the maximum power transfer theorem. So what we have 417 ohm. In software we are getting 410, and in actual practice, in actual laboratory, we are getting it to 427. And if we draw the graph, you will get very like change like 400 to 430. In between that you will get the resistance. So this is the way you can prove the maximum power. So maximum power is delivered from source to load when load resistance is equal to the internal resistance, or we can say Thevenin resistance of the circuit. So this is the way the practical is. So you have to fill this observation table, you have to draw the graph, you will get the readings. Thank you.